So, good morning. So, now the remaining couple of classes we will look at the very important aspect of how do we measure whatever we have talked about in micro nano scale energy transport. So, measurement is a very important step. So, we have looked at so many theoretical models to understand heat transport, flow transport and so on. So, when you finally have to prove that this theory works, so you have to do a measurement, you have to compare it with the theory and then show that the theory really predicts the measurement very well. So, therefore, I think in terms of priority, I think measurement gets the highest priority, followed by theory. The theoretical modeling is always supporting the measurement, and therefore, we have to always perform experiments even at small scales. It may be, however, very difficult to do experiments, to build small experimental setups, to take measurements of temperature, pressure, flow at micro nano scales. However, I think without doing that, the theoretical part becomes incomplete, right. So, as with even the macro scale, so unless you show a good agreement of your theory with experiments, nobody is going to buy your theory. So, this the same thing has to be also valid at micro nano scale without doubt, with only the exception that the experiments are far more difficult and you have to become use more sophisticated techniques to probe into the smaller scales. So, I think we will discuss a few aspects of measurement techniques. So, we will start with some micro scale measurement techniques and then we will end with the nano scale part, nano scale thermophysical properties. So, I think in the under nano fluids we already saw the thermal conductivity and viscosity measurement techniques using hot wire, transient hot wire probe and viscometer, right. So, those are not specific to anything in the nano or micro, but they are generic equipment. So, you can also use them for nano fluids. So, that I have not put that in this particular section, because this is only pertaining to measurements at the micro nano scale. Now, one of the first things that you want to start with the micro scale is once you fabricate a micro channel, for example. So, you want to calibrate the diameter or dimension of these micro channel, right. So, now let us assume that this micro channel is fabricated in such a way that you have a certain roughness, okay. You cannot avoid surface roughness. So, with a certain surface roughness which could be of the order of few microns, and also the diameter of this channel or the depth of the channel could be of the order of few ranging from few tens of microns to hundreds of microns, okay. So, therefore, this is the order of magnitude of micro channels that are currently existing, okay, that you can fabricate. But one is the fabrication technique or manufacturing technique, the other is how do you check these dimensions, okay. How do you check once you make a micro channel of diameter 100 microns that this is exactly 100 microns, okay, and what is the accuracy of such a measurement process. So, this is the most basic thing, that means given that you have a micro channel fabricated to you, given to you, so you have to estimate what is the dimension of this and similarly the roughness. So, you have to characterize what is the average roughness. So, we have seen that when we apply the reduced diameter theory, okay. So, in that case you have to know what is the order of roughness size in order to calculate the reduced diameter, okay. So, in such a case you have to have a measurement device to accurately calibrate, sense the surface roughness and also measure the roughness to a reasonably good accuracy. So, therefore, how are we going to do this? So, the issues that are required, when you talk about measurement techniques there are few of them. So, one is that fabrication of these micro channels is already a complex process. So, you have to either use, so we are not actually talking about those things. So, people working in manufacturing have to deal with these special issues in manufacturing or fabrication of micro and nanoscale materials. Okay. So, we are not talking about that, we are only looking at so generally, I mean, if you take any manufacturing process at micro nanoscale, so you have to have very strict quality controls. So, it is not just making a channel with this size, you have to also make sure that if you need a surface which is smooth or a surface which is of a defined roughness, so you have to make sure that the surface texture is properly made, okay, and the dimensions are more or less measured satisfactorily, you know, to to the desired accuracy, and then this is what is going to be having a biggest impact when you do the flow measurement process. For example, we all know that as far as the micro channels are concerned, if it is a gas flow, then you have a slip depending on the order of the dimension. Okay. So, if your Knudsen number is approaching close to 0.1, so you will have a slip at the wall, and this slip is very much affected by the kind of roughness. So, as we have talked about the accommodation coefficients, so you can have either a diffuse reflection of these molecules at the surface, or you can have a specular reflection, and according the accommodation coefficients will change, and this will decide what is the kind of slip that you happen to have at the wall. So, therefore, the surface roughness quality of this surface texture becomes very important in micro channels. Okay. And again, in micro flows, the entire flow is now influenced by the presence of the wall boundaries. Okay. So, therefore, any imperfections in the manufacturing process is now going to impact the fluid flow phenomena itself. Okay. So, you might have a theory, okay, for a certain approximation. Now, when you make this particular channel, so it will not be conforming to that, okay, and therefore, it becomes even more difficult to validate your theory if your experimental setup is not well made. So, these are some techniques, I would say, coming from the manufacturing process itself. Okay. So, therefore, very important first step process in measurement is the measurement of the micro channel dimension and its roughness. So, if you are given a micro channel from the manufacturing section, so what you have to do is first ensure that if you had asked for 100 micron channel, you get it 100 micron, plus of course, there is always tolerance, manufacturing tolerance, which has to be accounted, but you have to have a method to ensure this dimension is in the reasonable limits. So, what are the different ways of measuring the dimension? It is not like you take a small scale or vernier caliper directly and go and check this, because the order of magnitude of these dimensions are smaller than what you can sense through vernier calipers or screw gauge. Okay. So, you cannot resolve say 10 microns and 20 microns in your screw gauge. So, therefore, what are the practical methods to do this? So, one is what is called by filling this particular channel or capillary with a denser liquid like mercury. Okay. So, generally if you are talking about a capillary tube, so capillary tube may be of dimension less than a millimeter and the order of few microns, or a micro channel. So, what do? Is we simply weigh the tube first, the empty weight. Now, we fill it with mercury. Okay. So, once you fully fill this, you again weigh it, reweigh it, correct. So, and then you take the difference. So, now you know what is the volume. So, you know the density of mercury. So, you know the mass. So, therefore, you can calculate simply the difference between these filled weight and the empty weight multiplied by the corresponding density should give the volume. So, divided by the corresponding density should give you the volume. So, therefore, this volume gives you the total volume of this capillary tube inside section. So, since you know the length in a much more precise manner than the diameter, because the length will be usually of the order of centimeters, okay, compared to the diameter which will be in the micron range. So, therefore, now with this method you can estimate what is the diameter of this channel, right. So, the diameter that you get here will be accounting also for the surface roughness, because this is actually what the fluid is filling. Okay. So, for example, if there are some some small defects in the surface of the tube, okay, some cavities. So, the liquid can also fill that, and it will also tell you, I mean the volume based on that small cavity. So, therefore, this is although not very perfect tool, okay, with a reasonable accuracy you can estimate what will be the diameter of tubes. Okay. So, therefore, from the advantage point of view, this method is one of the simplest you can think about. Okay. You do not have to invest in any equipment, all you have to do is fill with either water or mercury, because more denser it is better, you can sense the the mass difference much better way, and also it enables a very accurate determination of the flowing area along the whole length, and what you need is only a precision balance. So, balance should be fairly sensitive, maybe to the third or fourth decimal point. So, you should be able to resolve the mass of this. Okay. So, generally to the limitation of this method is to obtain a good accuracy of measurement for a very small tube. Suppose you are now going to the order of tens of microns. Okay. If you want to use this method, so in order to have a significant volume, so you have to have very long tubes. Okay. Only then the difference between the initial and final weight will be somewhat resolvable. Okay. If this is of the order of fourth or fifth decimal point, so again your precision balance may need to be more precise or more accurate. Okay. So, therefore, this can be used to a certain range of diameters, but if this falls short of say by the diameter is of the order of 10 microns, then you have to have very long tubes in order to fill the mercury throughout and get a good estimate of diameter. So, this is anyway one of the simplest methods. The other method is how we do it is by flowing a liquid through capillary. Okay. So, this flow, now this case mercury filling is just does not require any pump or anything, you just have to fill it manually and then weigh and check the difference. So, the other case you are going to actually pump liquid, it could be water or mercury again, and you are going to pump it through the capillary. Now, the way you are going to pump it is that, since you know that in a capillary tube, so you can actually use the Poiseuille's law. Okay. So, if you are especially using liquids, okay, so there is no problem with the slip boundary condition, therefore, everything is continuum. So, whatever fully developed flow for the macro channel or macro capillary, the same thing can be applied here. So, the Poiseuille law is still valid. That means, if you measure the pressure difference across the tube, so you will be able to measure what is the flow rate. Okay. So, average velocity, and therefore, you will know the flow rate, and from which you can actually again estimate the mass, because till what time, what is the amount of time that this flow was happening through this tube, and therefore, from this you can calculate the mass. So, this is an indirect way of calculating mass. So, you do not have a balance, precision balance, because sometimes if the diameter is too small, then even a precision balance may not be able to do the good job. So, therefore, the general process is we flow either water or mercury. Now, mostly since you have very tiny capillaries, you can achieve constant pressure drop, which will generate a constant flow rate through the channel. So, and we know from the Poiseuille law we can relate the flow rate as a function of pressure drop. So, therefore, if you measure the pressure drop, okay, using a differential pressure transducer, and you know what is the amount of time for which this liquid is been flowing. So, you can actually calculate the mass flow rate, and therefore, mass, the exact amount of mass of the liquid filling the tube. Okay. So, once you fill the tube, so you do not completely fill the tube, you pass the fluid, because if you have reasonably long tube, so you can count few milliseconds or maybe a second, and then at maybe a smaller pressure drops you can let the flow go go through at a fairly low flow rates, and then by the time the flow reaches the other end you stop it, you know how much time you have filled it. Okay. So, calculate the mass, and again this is used for, taking the difference between the initial and the final mass, and you should be able to estimate again the diameter based on that. The only difference here being from the previous case, the previous case is a static one, you completely fill it and then you weigh it. In this case you flow the liquid by using a pump, and then you do not use a precision balance now, but you use Poiseuille's law to estimate the mass. Okay. So, what is the advantage of this technique over the other? So, since you are avoiding a precision balance, right. So, therefore, the least count, and therefore, the precision of the balance is not going to play a big role in determining the size of the tube to a great accuracy. So, it is only going to be the pressure drop that you will measure, and usually these tubes, the smaller the tube, the larger is the pressure drop. So, the pressure drop is resolved fairly accurately without any big problem. Okay. And you also know the Poiseuille's law is very accurate. So, therefore, the accuracy of this method is usually much better than simply weighing it. So, the technique can be therefore useful to reduce the uncertainty in the determination of the inner diameter to about up to the order of plus or minus 0.2 microns. Okay. So, that means you can actually determine it with a very high precision. The precision can be plus or minus 0.2 microns, and the average inner diameter for a tube with a, for example, a nominal diameter of 150 micron could be of the order of plus or minus 0.113%. So, this is the order of accuracy we are talking about with this particular method. Okay. So, only thing, what are the limitations is that for very small flow rates, that means if you have very low pressure pumping power, okay, with the pump. So, and you maintain a very small flow rate. So, this might actually take a very long time for liquid accumulation, especially if your tubes are quite lengthy. Okay. So, and again depending on the working fluid, so you assume that there is no evaporation, all this is a adiabatic case, but in reality if you use water for example, depending on the surrounding humidity, so there could be some losses due to evaporation. So, in that case there will be some actually water vapor that could be accumulated inside, or there could be loss of water. So, again that will be causing some errors in the difference in the weight. So, especially when you are talking about smaller micro channels, so these losses due to evaporation and so on might affect the diameter measurement fairly to a great extent. Okay. But nevertheless, this is a better method than simply weighing the channel itself. Now, if you want to go to a more detailed descriptive method, so that means I want to look at the microstructure of the surface, okay, how the surface roughness is there, what is the profile of the surface roughness and how it varies. So, none of the previous two methods will work, because all it tells you is only the wetted diameter, right. So, okay, the wetted diameter can come out of that particular theory, but if I want to probe further into the nature of the surface roughness, okay, and I want to maybe make tubes of the order of say few microns, 2 or 3 or 4 microns, then those two methods again will have serious problems. So, therefore, in such a case we make use of the scanning electron microscopy, SEM. Okay. The scanning electron microscopy is usually available if you go to either the chemistry lab, physics lab or materials engineering. So, usually they use this when they kind of synthesize a new material at the nano scale, and they immediately have to characterize this material. Okay. So, they do use different techniques for characterization. One, they have to first identify what is the size distribution and how it is actually appearing. So, the physical appearance. So, that is done by using the scanning electron microscope. Okay. So, then they also look at the chemical nature of the constituents of this particular. So, they do spectroscopy, X-ray diffraction, Raman spectroscopy, all this to tell what is the chemical nature of this particular material that they synthesized and to confirm whether this is this. Okay. Suppose I make graphene, okay. I want to make sure, how do I make sure that what I get out of my procedure is graphene. So, for that they have to run through the Raman spectroscopy for example, and they have to detect a peak at a particular wavelength, okay. That confirms that is the signature of graphene. So, but before doing that you have to understand how these graphene looks, okay. What is the size distribution, so how they appear. So, to do this this kind of an optical imaging, so since we cannot do this under a normal microscope, so you use the scanning electron microscope to do that. Now, the same scanning electron microscope can also be used to look at the surface roughness and also to measure the diameter of this kind of capillary tubes or microchannels. Okay. But however, you should remember this can be possible only either the existing channel you cut cross section small portion and put it under the microscope and have a look at it, or it should be optically accessible. Okay. So, you make a rectangular microchannel with an optical axis on the top, so that you can probe into it. But if it is completely opaque from all directions and you synthesize a microchannel which you simply cannot cut, so how will you then determine the diameter? So, then it becomes difficult to use even this method. Okay. So, but the thing is, once you take a section or you make an optical axis, so the profile of the channel cross section can be determined with a very high resolution. Okay. So, this is of course, because you are now able to resolve to the order of few nanometers with the SEM, okay, few nanometers. So, therefore, any small tiny burr that appears on the surface even of the range of nanometers can be easily resolved. Okay. The advantages is, so if you are doing using this method, the dimensions of the channel cross section and topology of the roughness can be determined with a very good accuracy. However, what are the limitations? So, when you are talking about closed microchannels which are not optically accessible, that is they are opaque. So, many cases you are having metallic microchannels, so which are closed from all sides. So, in that case you cannot simply cut it or you cannot put it under the microscope and get it. So, you cannot get any information from such cases. So, just to show a schematic of how the scanning electron microscope looks. Okay. So, there is a separate theory for this, and again the setup is not fairly that large, but also it is reasonably large. You need to have dedicated facility for that, a room for that, and you have to maintain the ambient conditions at a constant temperature and humidity. So, you have to invest certain amount of money in maintaining this kind of microscopes. Okay. So, therefore, the first part was concerned with respect to the measurement of dimensions, right. So, depending on the access that you have. So, if you do not have access to SEM, then definitely you have to resort to one of the first two methods. But if you have an optically accessible microchannel and also an access to an SEM, obviously I would go for the third method, which will give you a more detailed picture of about the surface as well as the dimensions, correct. So, now the next important quantity of measurement is pressure. Okay. So, of course, when we are talking about pressure measurement, so we are talking about generally pressure drop here. Okay. It is not just the absolute pressure that we are interested in. So, any microchannel we are always interested in what is the pressure drop across this microchannel, and usually the good thing is these pressure drop values are not very small like the value of the dimension itself. So, there is nothing really specifically problematic with using an existing differential pressure transmitter which can measure the pressure drop for a bigger channel and using it for a micro channel. Usually only the range has to be customized, the ranges should be higher when you are going for a micro channel. But however, there are other issues which makes this measurement process a little bit more uncertain. So, for example, for one thing, you know, the entry and exit losses, that is the contraction and expansion losses are very significant in a micro channel compared to a larger channel. So, therefore, when you it depends to a great extent where you put this pressure tappings. So, just to give an example, so if you are fabricating a micro channel like this, okay. So, you usually have a inlet manifold, okay, through which you have a flow of liquid and you have an outlet manifold to which you take out. Now, where do you put the pressure tappings? Obviously, you know, you have to put a pressure tappings where you have a sufficient contact area, okay. So, generally we put it somewhere here or here, okay. So, therefore, the differential pressure that you measure, okay, is actually not within only the micro channel, but from the manifold. So, therefore, the actual pressure difference that you are measuring also includes the contraction losses here and the expansion losses here, the entry and exit losses. So, this is usually the problem, and these are not very small values which you can ignore, right. So, therefore, if you want to really only measure the exact delta P from here to here, so this is a very difficult process, because you cannot put a pressure tap here and here, this is the flow path. The flow path itself is very small, okay. So, you cannot simply put a pressure tap there and you cannot disturb the flow, okay, but you are interested in only delta P across this tube and not across the manifolds. So, therefore, you have to find a method to eliminate the contraction and expansion losses. So, one simple way is, of course, theoretically you might know from the correlations. So, what is the value of delta P at the inlet, what is the value of delta P at the outlet, right, from the entrance and exit losses. So, but these are approximate things, they are not applicable to all kinds of micro channel shapes, okay. So, therefore, but you can probably use that and you can reduce the delta P. So, you will be measuring the overall delta P and you will be subtracting delta P in and delta P out using theory, but this is a very rough approximation, correct. So, therefore, what will be a better way to do this? So, therefore, what we will do is a method called tube cutting method. So, that means, so now you take a big tube, a large tube, and you measure the delta P like this, okay, and now you cut this tube to a smaller length and again measure delta P and take the difference between the delta P's. So, when you take now the difference between the delta P's of the longer tube and the shorter tube, what happens? The common factors are the inlet and exit losses. So, these are going to be the same whether it is a long tube or short tube, as long as the tube diameter is the same. So, therefore, that will get automatically eliminated, okay. So, from which you can calculate your friction factor, which will give you the pressure drop only within the tube and not the including the entrance and exit losses. So, this is one of the very simple ways, you know. So, there is no technology here really used, all you need to first do is take your actual tube, measure the delta P and then either cut this tube or make another tube with the same diameter, okay, and again measure delta P for that, take the difference between the two, right. So, this will now eliminate all your uncertainty with respect to the entrance and exit losses. Is that clear? So, this method is called the tube cutting method. Okay. So, as it says, this technique consists of repeating the same mass flow rate conditions of a long tube in the short one with the same inner diameter. So, that means if you want to measure the delta P, again you have to make sure the mass flow rate is the same. So, because your delta P is a function of flow rate. So, since the effect of the minor losses is approximately identical for both tubes, so we have to just only do a subtraction of delta P between the longer and the shorter tube. So, and how do you select it? The short and the long tube can be selected from a set of identical tubes. So, if suppose you have just tubes, so you can simply select from the same lot, or you can cut the longer one and then get the shorter one out. Now, therefore, if you see the pressure distribution, so strictly speaking, if you are looking at incompressible flows, okay, and if you assume the flow is fully developed, how will the pressure distribution look? It should be straight line, correct. So, that means your dP by dx should be a constant, that is where the Poiseuille's law is valid. Okay. So, but this curve actually shows in a realistic case where, for example, if you have compressible effects, okay, so you may not have a constant pressure drop, pressure gradient. So, therefore, there it will be deviating from a linear curve. So, usually this method will give you very accurate results as long as you have a linear variation of pressure, the linear drop. Okay. So, this is valid if you are mostly focusing on incompressible flows and fully developed flows, but if you have compressible effects, then this method will fail, because now your pressure difference is going to be different in different regions. So, therefore, if you have a longer tube, so you are therefore talking about a pressure difference which is maybe here this much, right, and if you take the shorter tube, so your pressure gradient is going to be somewhere here, delta P. So, therefore, this difference will give you a different value, okay, which is not corresponding to the same pressure gradient. Okay, your dP by dx is going to be different in different regions. So, therefore, you cannot use this tube cutting method if you are working with, for example, compressible flows. Okay. So, therefore, what are the limitations of this particular method? So, this method can be applied correctly when the pressure drop in the tube is linear as for incompressible flows. Okay. So, generally if you are talking about ratios of P in by P out, they are reasonably small, then this could be okay. Okay. If the pressure distribution is not linear, as in the case of compressible flows, the method cannot be applied, right. So, therefore, there is a shortfall of this method, you cannot extend it to all kinds of flows, especially slightly higher Mach number flows or very large pressure ratios or compressible flows. So, in such a case, so you have to use other techniques. So, the other technique, one such technique is called the pressure sensitive paint. Okay. So, this is not so commonly used in our institute, for example, but and this also requires highly sophisticated equipment compared to a simple differential pressure transmitter in the earlier case. So, in the case of pressure sensitive paint, we rely on applying a coating, okay, so which are like molecular sensors. Okay. So, this what you do is you shine a light, it could be a normal white light or it could be a laser light, and these sensors that you coat on the paint that you coat on the wall. So, this will respond to the light. Okay. So, the beam that is emitted from this particular coating, okay, is responsive to the intensity of light that you shine from outside and also on the pressure exerted by the molecules on the surface. Okay. So, for example, if the pressure is on the higher side, so this intensity of emission coming from the paint will be higher. So what you do is you calibrate it with a normal surface, you apply the paint. Okay. So for example, you can have a square micro channel, you apply the paint on the wall of the micro channel, you pass the flow at a certain pressure, you record the corresponding intensity coming out, and then you increase the pressure. So with variation with respect to pressure, you record what is the intensity of the emission. So therefore you can build a calibration, and with that you go to the actual case. Now you can record the actual variation in the intensity across the tube or the micro channel length, so along the micro channel length. So from that calibration you convert this back into pressure. So this is the method. Of course, this is not a very straightforward method. So these are non-intrusive, however, because you do not put any pressure tapping and pressure probe into the channel, but you are just imaging this from outside, and you are also probing this by using a white light or a laser light which is kept outside. Okay. So all you are doing is only applying this the sensor, which is the paint, onto the wall. So the non-intrusive measurements, PSPs are optical molecular sensors which enable the measurement of pressure over surface. So when you excite this molecular sensor by an external light source and defined wavelength. Okay. So if you are using optical white light, then you should know what wavelength you are operating, or if you are operating a monochromatic light source like laser, you know exactly the precise wavelength that it is coming. So the luminescent molecules from which the surface of the channel cover will be coated will emit luminescence of a longer wavelength. So it is just simply luminescence, which is meaning there is an emission coming from these molecules which is having a different wavelength than the wavelength that is falling. There is a correlation to that. Okay. So if you generally use a particular lambda, so the emitted wavelength will be greater than this lambda. So you basically filter out, you use some processing tools where you filter out all the noise, and then you look at only the intensity of the emission of coming from the molecules, and this intensity is now sensitive to how much pressure the molecules apply to that particular surface. Okay. So primarily the existing pressure sensitive paints respond more to oxygen molecules than other molecules. Okay. So therefore it depends. So if you are using only oxygen gas as the working fluid, then this kind of method will work, but if you change it to nitrogen or argon, okay, or air in general, then this will not work. Okay. So the existing pressure sensitive paints are mostly sensitive to oxygen molecules, and therefore for this reason only gas flows can be used with this method. So specifically an increase in the oxygen concentration causes a decrease in the intensity of luminescence, so and so on and so forth. So therefore we calibrate it first to derive a calibration curve between the pressure and the intensity of the emission. So once you calibrate, then you will be able to get back what is the pressure. So what are the limitations? So this technique is based on oxygen quenching, so therefore it cannot be applied to test other pure gases like nitrogen and helium. Okay. The pressure sensitive paint also needs a transparent axis. So it needs an optical axis, because what you are doing is, so you have a LED, so which is emitting light, and you have a photo detector or a camera which is going to detect the intensity coming from the surface. So but it has to pass through the optical axis, and then it should reach the surface, and from which again the emitted light should travel through the optical axis and reach the camera. So for this your surface should be optically accessible. So if you have a opaque surface closed from all ends, then again it is very difficult to do this, use this technique. So passages which do not have a transparent side cannot benefit from this optical technique. Okay. So we will look at therefore one more last method for measuring pressure before we stop the pressure measurement. So the third method is called the optical lever method. Now, this is a slightly bit more sophisticated, I would say, methods than the other two methods. You need a lot of investment to do this, but with this method you can actually do for a large range of working fluids without any restrictions. Okay. So, now what we do is in a micro channel, so you have all these pressure tappings. So, we take all these pressure tappings to a silicon membrane like here. Okay. So, this is a flexible membrane. So, this membrane will deflect. Okay. So, this deflection is proportional to whatever pressure that is falling on this membrane. So, for example, if you connect a few pressure tappings onto this surface, so the entire surface will deflect at a differential amount depending on what is the local pressure, correct. So, now what we do is we now have to have the laser source, and we have to have a sensor which can detect what is the intensity of the laser light that is reflected or deflected from the silicon membrane. Okay. So, a laser source will be illuminating light, laser light onto the membrane. Now, depending on the deflection, so the angle of the deflected light, that is the deflected light coming from the membrane will be different. Okay. So, if there was no deflection, it will reflect in a particular angle. Okay. Now, due to deflection, this angle will change either in this way or this way. So, there is a sensor, okay, which is placed there, which can actually also move, which can be movable in different directions. So, it can actually traverse this way or this way, and it will detect the intensity which is deflected from the membrane, and therefore, from that it can detect what is the angle at which it is actually coming from. So, depending on this angle can be calibrated to the actual pressure. So, initially you do a calibration. So, you know what is the exact pressure with a pressure probe, and then you know what is the angle which is picking up. So, you build a calibration as a function of this deflected angle, and later on once you know what is the deflected angle, you can get back the pressure. Okay. So, this is the basic technique. So, the deformation is measured recording the change in the deflection angle of a fixed incident laser targeting the membrane surface. The change in the deflection angle is measured by a sensor, it is a photodiode sensor which can be precisely moved and positioned. So, based on this principle, the integrated pressure sensor can be produced. Okay. So, the sensitivity of this pressure sensor can be easily adjusted by changing the spatial resolution. Okay. So, if you want it to be very sensitive, place it very close. Okay. If the deflection is fairly large, you can keep it further away and you can get reasonable accuracy. Okay. And the uncertainty can be ranging from anywhere between plus or minus 2.4% to 13%. Okay. So, but this does not have any constriction over what kind of working fluids you use, right. So, compared to the pressure sensitive paint and the tube cutting liquid, so it can be a compressible fluid or it can be any kind of fluid, but you can use this method to measure the pressure.
Across the cross section it may vary because due to flow instability it may be possible that at some position the deflection of the membrane is more and at the other place the deflection is this. Is it possible in this case that across the cross section?
Yeah. So, actually what we can do is that one simpler way, you do not have to really have ports. So, you are talking about a micro channel like this. Okay. So, you have the flow. Okay. Now, this can be attached directly to this membrane. So, then the fluid locally will be sensing, it will be exerting the pressure onto the membrane directly. So, you do not have to actually, you can also take ports, you can also make ports and connect it like to the different points in the membrane. Okay. So, it is depending on how you want to do it. Okay. So, if you do this, then it will sense the differential deflection. So, each point on the membrane will have a different deflection. So, depending on that it can get the pressure. but what it does is it is only directly measuring the pressure in the channel and we are not measuring the delta P. So, it is actually measuring the local pressure. Okay, that is the advantage of this technique. So, any differential pressure measurement will now involve the entry and exit losses. So, we will stop here and next class we will look at temperature and velocity measurements. Okay.